Good morning everyone. In the previous class, we discussed decomposition methods which belong to the class of direct methods for solving a system of linear algebraic equations and explained how we can solve a system Ax is equal to b by Doolittle method and Kraut's method. In Doolittle method, the decomposition is in the form A equal to L into U, where L is a unit lower triangular matrix and U is any upper triangular matrix. Whereas, in Kraut's method, the factorization of A in the form LU consists of unit upper triangular matrix and any lower triangular matrix. And we also mentioned about Cholesky's method, wherein we stated the result under which Cholesky's decomposition is possible. So, we said that if A is a real symmetric positive definite matrix, then A has a unique factorization of the form L into L transpose, where L is a lower triangular matrix with positive diagonal entries. Here A is a square matrix. So, we shall see how we can solve a system of equations using Cholesky's decomposition method. So, let us consider the problem of solving the system Ax is equal to b. So, let us look at the matrix A. We observe that A is a real matrix, it has real entries. It is a symmetric matrix because we say that A12 is A21, A13 is A31, A23 is A32, and so it is a symmetric matrix. In addition, we find all the leading principal minors. The leading minor of order 1 is 1 and it is positive. A leading minor of order 2 is determinant 1, 2, 2, 8 and that is 4, that is again positive. And a leading principal minor of order 3 is determinant of A, and when we compute determinant of A, it turns out to be 42, which is again positive. So, all the leading principal minors are positive and therefore, A is a real symmetric positive definite matrix and therefore, matrix A has a unique factorization of the form L into L transpose, where L is a lower triangular matrix with positive diagonal entries. So, we consider A in the form L into L transpose. We have to solve the system Ax is equal to b. So, L transpose x is equal to b. So, if we set L transpose x as z, then the system becomes Lz equal to b. So, we observe that when we set L transpose x is equal to z, L transpose is an upper triangular matrix. So, we have to solve a system of equations where the coefficient matrix is upper triangular and therefore, we solve this system by backward substitution. So, on the other hand, when we have this system Lz equal to b, then L is a lower triangular matrix and therefore, we solve this system by forward substitution. So, first solve Lz equal to b by forward substitution, determine the components of vector z, use that information here and solve L transpose x is equal to z and obtain the unknown vector x. And that will give you the solution of the system using Cholesky's decomposition method. So, let us now see how we can factorize A in the form L into L transpose. What is the property of this matrix L? L is a lower triangular matrix with positive diagonal entries. So, keep this in mind. So, let us take L to be a lower triangular matrix in the form L11, L22, L33 appearing along the diagonal and the other entries are written below the diagonal. Its transpose is going to be an upper triangular matrix So, we write down L transpose. So, the column entries will become the first row entries, the second column entries will be the second row entries, the third column entries will be the third row entries. So, we multiply the two. So, first column, the first row into the first column will give you L11 square. Second row, first column will give you L21 into L11 plus 0 plus 0. So, it is L21 L11. Then the third row into the first column will give you L31 into L11 and the rest of the two terms will be 0. Then we consider second row into the first column, that will give you L21 L11 plus 0 plus 0. So, that is what is written here. And then the second row into the second column, etc., you compute the product of the two matrices L and L transpose, and you will observe that the resulting matrix is this, and this has to be equal to the matrix A, and therefore, the corresponding entries are equal. So, we equate the corresponding entries and try to determine the Lij which appear as unknowns in the matrix L. So, we start with the first column entries in the resulting matrix. So, L11 square must be equal to 1, and so L11 equal to 1. Why do I take only the positive root? What is L11? It is the first row, first column element. It appears as a diagonal element in the first row, and therefore, when we wrote down the result under which a matrix A can be decomposed in the form L into L transpose, where A satisfies the conditions that it is a real symmetric positive definite matrix, we said that the entries on the diagonal on the matrix L are all positive, and so we choose the positive root here. So, L11 is 1. Then we move over to the element L21 L11, and that is equal to the corresponding entry here, which is 2. We have just now computed L11. So, that gives you L21 to be 2, and then the entry here, which is L31 L11, and that must be equal to 3. So, use the fact that L11 is 1, that gives you L31 equal to 3. So, you have been able to determine L11, L21, L31, namely you have been able to determine the entries in the first column of L, namely the entries in the first row of L transpose. Now, you move over to the entries where you have already determined L11, L21, you have already determined L31, L11, because the entries which appear here are the same as the entries which appear here. So, we need to make use of the values which correspond to the values of these entries in the matrix A. So, I consider L21 square plus L22 square and equate it to 8. L21 is already known, which is 2, and so L21 square is 4, and so this immediately gives you L22 square to be equal to 4. So, L22 is 2, again we take the positive square root because L22 appears as a diagonal entry in the second row. Once L22 is determined, we move over to the next entry here, which is L31 L21 plus L32 L22, and that is equal to the corresponding entry 22. All the others are known except L32. So, when we substitute and solve for L32, we get L32 to be equal to 8. So, what is it that we have got at this step? By equating the entries in the second column below the first row to the corresponding entries in A, we ended up with the entries L22, L32 in the second column of L, and therefore, on the second row of L transpose. The only entry that remains to be obtained is L33, and so we make use of the information here, which says L31 square plus L32 square plus L33 square is equal to 82, and therefore, substitute for L31, L32, and that gives you L33 square to be 9, and hence L33 is equal to 3. Here again we take the positive root because L33 appears on the diagonal in the third row, and we want to determine L in such a way that its entries along the diagonal are positive, and therefore, we choose the positive square root when we get equation for L11, L22 or L33 because they appear on the diagonal. So, we have determined all the unknowns which appear either in L or in L transpose, and hence we write down the matrix L, and we first have to solve the system Lz equal to B. So, I consider Lz equal to B. I write down L, namely L11, L21, L31, L22, L32 and L33, and Z has components Z1, Z2, Z3, and the right hand side vector B is given here. So, when we have a lower triangular coefficient matrix in a system of equations, then we make use of forward substitution and obtain the solution. So, the first equation gives you 1 into Z1 equal to 5. The second equation gives you 2Z1 plus 2Z2 is 6. Z1 is already known, so this gives you Z2 as minus 2. Then we move over to the third equation, which gives 3Z1 plus 8Z2 plus 3Z3 equal to minus 10, and Z1 and Z2 are known. So, from here we solve for Z3 and that turns out to be minus 3. So, the unknown vector Z is now determined. So, we have to now solve the system L transpose X is equal to Z. Here Z is known because we already have solved for it. X is an unknown vector which has to be obtained. Right? The coefficient matrix for this system is L transpose. So, solve the system L transpose X is equal to Z. So, write down L transpose. What is it? It has entries L11, L12, L13, then 0, L21, 0, L22, L23, 0, 0, L33 multiplied by x1, x2, x3 is equal to the vector Z that you determined, namely 5 minus 2 minus 3. And you observe that in this case the system has coefficient matrix to be an upper triangular matrix, and therefore, you have to solve this system using backward substitution procedure. So, you start from the last equation that gives you 3x3 is minus 3. So, x3 is minus 1. The last but one equation gives 2 times x2 plus 8 times x3 is minus 2. You just now computed x3, use that information, that gives you 2x2 equal to 6. So, x2 is equal to 3. And you move over to the first equation, which gives you x1 plus 2x2 plus 3x3 is 5. So, use the values of x2 and x3 in this, that gives you x1 equal to 2. So, your unknown vector or the solution to the system of equations Ax is equal to b is given by x is equal to x1, x2, x3, and they are given by 2, 3 and minus 1. If you substitute these values in the given system of equations, you will see that they are identically satisfied. It is just a check on your computations. So, we have obtained the solution of the system Ax is equal to b using Cholesky's decomposition method. We had ensured that A satisfies the conditions, namely it is a real, symmetric, positive definite matrix, and therefore, it possesses a unique factorization of the form LL transpose, and in determining the matrix L, we have taken care to see that the diagonal entries on L are positive. So, we now know how to solve a system of equations by decomposition methods, namely factoring A in the form L into U with appropriate L and U depending upon what decomposition methods that we want to use to solve the system. And these three methods, namely Doolittle method, Kraut method and Cholesky's method, they belong to the class of direct methods for solving a system of equations Ax is equal to b, where A is an n cross n matrix. So, we now move on to another type of direct methods, which is referred to as Gauss elimination method. So, we shall try to understand Gauss elimination method and see how we can solve a system of equations by this method. So, we consider Gauss elimination method. What does this method do? Given a system of equations Ax is equal to b, it employs elementary transformations and reduces this matrix A to an equivalent system, which is u into x is equal to, say, some b cap, where u is an upper triangular matrix. So, you start with the system Ax is equal to b and apply elementary row operations on the rows on the matrix A and reduce the matrix A to an upper triangular matrix U. So, you end up with an equivalent system Ux is equal to b cap, and you know how to solve this system, because the coefficient matrix is an upper triangular matrix. And so, you employ back substitution procedure and solve this system and determine what x is. So, Gauss elimination method involves two steps. The first step is reducing a given matrix A to an upper triangular matrix. The second step is employ back substitution method and solve the system Ux is equal to b cap. So, let us try to understand Gauss elimination method and see how a matrix A can be reduced to an upper triangular matrix using elementary row operations. So, we shall illustrate the details by taking a system of three equations in three unknowns. It is easier to understand. The method works in the same way for a system of n equations in n unknowns. Let us consider a system of three equations in three unknowns given by a11 x1 plus a12 x2 plus a13 x3 equal to b1, a21 x1 plus a22 x2 plus a23 x3 is b2, a31 x1 plus a32 x2 plus a33 x3 equal to b3, which can be written in the form Ax is equal to b. So, what is it that we do in reducing this matrix to an upper triangular matrix? What does that mean? If we have to make this into an upper triangular matrix, then I must have the entry here, which is the coefficient of x1, to be 0, and also the entries which are coefficients of x1 and x2 in the third row must be equal to 0. So, I must perform elementary row operations in such a way that the entries which are rounded here, they must be made into zeros. So, let us do the following. The first step is the following, namely I keep the first row as it is. I call this row as a pivotal row at this step, and the coefficient of x1 is what is called the pivot. So, I take the first equation for the unknown x1 and therefore, I call its coefficient as the pivot and call the first equation as the pivotal equation. So, I keep the first equation as it is and write down a11 x1 plus a12 x2 plus a13 x3 equal to b1. What do I want? I want to convert this system to an upper triangular system. As I already remarked, I want the entry which is the coefficient of x1 in both the equations, namely the second and the third equations, to be 0. So, I perform the following row operation. What is it that I do? I multiply the first equation, maybe I call this as row 1, this is row 2 and this is row 3. So, I shall multiply the first equation R1 by A21 by A11 and subtract it from the second equation R2. So, my new R2 is such that it is the old R2 minus A21 by A11 times R1. So, my new R2 replaces the old R2. So, this is one of the elementary transformations. What is it? Multiplying an equation by a scalar and adding it to another equation. So, I am adding it to another equation and taking the coefficient as negative. So, I say I am subtracting it from the second equation. So, I have performed an elementary row operation and replace the second equation by the following, namely it is R2 minus A21 by A11 into R1. Let us see what happens when we multiply the first equation by A21 by A11. So, this becomes A21 by A11 into A11. So, here we will have A21 x1. We are subtracting it from A21 x1. So, the coefficient of x1 will be 0 in the new second equation at this step. Let us look at this. What are we multiplying? We are multiplying the first equation by A21 by A11. So, A21 by A11 into A12, we are subtracting that from A22, and so let us call this as A22 at the first step. So, the coefficient of x2 now will be A22 minus A21 by A11 into A12, and I call that as A221. That is the coefficient of x2. Let us go to this. So, I will subtract from A23 A21 by A11 into A13. Let us call that as A231, and that is going to be the coefficient of x3 in the second equation. What about this? This will be B2 minus A21 by A11 into B1. Call that as B21. And therefore, when we perform this, I will have my equations to be as follows. The first equation remains as it is. It is the pivotal equation. So, I take it as it is. And I have performed an elementary row operation, and as a result the coefficient of x1 in the second equation is 0, the coefficient of x2 is A221. So, I write that here, and the coefficient of x3 is A231 and the right hand side is B21. So, this is my new second equation. I do the same thing with the third equation, namely I have to make this entry 0, coefficient of x1 in the third equation to be 0. So, what do? I multiply equation 1 by A31 by A11 and subtract it from the third equation. So, I perform another elementary row operation involving the third row and the first row. So, what do? I take the first equation, multiply that by A31 by A11 and subtract it from the third equation. So, the first term, namely the coefficient of x1, will be such that it is A31 minus this, and therefore, it will be 0, and so coefficient of x1 will be 0 in the third equation. What happens to the coefficient of x2 in the new third equation? It will be A32 minus A31 by A11 into A12. And then call this as A321. And what about the coefficient of x3? You will subtract from A33 the product A31 by A11 into A13 and call that as A331. What about the right hand side? It will be B3 minus A31 by A11 into B1 and call that as B31. So, at this step your new third equation will be A321 into x2 plus A331 into x3, and that is equal to B31. So, you have completed your step 1, where you have used two elementary operations, one involving row 2 and row 1, the other involving row 3 and row 1. And the resulting system is something like this. Wherein you see that the coefficient of x1 in the second and the third equations are made 0. If you have more equations, say if you have n number of equations in n number of unknowns, what is step 1? Step 1 is to use elementary row operations in such a way that the coefficient of x1 in all the rows below the pivotal row are made into zeros. That is what we have done. Now, we move over to step 2. What is step 2? At this stage, we do not touch the first equation, we keep it as it is and regard the second equation as the pivotal equation. And we call this coefficient, which is the coefficient of x2, the second unknown, where the second equation is the pivotal equation at this step, as the pivot at this step. And then what do I want to do? Keeping this as the pivotal equation, I should make the coefficient of x2 in all the other equations which lie below this equation into zeros, making use of elementary row operations. Here I observe that I have one equation and the coefficient of x2 in the third equation is A321. So, I must make this entry into 0 by an elementary row operation. So, when I do that, I will have at the second step my equation to be A11x1 plus A12x2 plus A13x3 equal to B1. And my second pivotal equation will remain as it is. And then my third equation will be such that I have to make this entry into 0. So, what should I do? I must do an elementary row operation. What is it? I must take, so here this will be my second equation, this is the first equation and this is the third equation. So, I keep the first equation as it is, the second equation as it is, but when I come to the third equation, what do? My new third equation will be such that it will be obtained by the following. Multiply the second equation by A321 by A221, A321 by A221, and subtract it from the third equation. So, when I multiply this by A321 by A221, I will have A321. When I subtract it from the third equation, which has coefficient A321, it will be 0. And therefore, what happens to the coefficient of x3? That will be A331 minus A321 by A221 into A231, and I call this as A332. So, my equation here will be A332 into x3 will be equal to. So, I have to do the same operations on the right hand side. So, I will get, what will I get? B31 minus, I am multiplying the second row by A321 by A221, and so this multiplied by B21, and that is the new B32. So, I end up with B32, and my third equation is going to be this. So, what is the elementary operation? R3 minus A321 by A221 of R2 gives me the new third row, namely R3. So, it is very important that at every step you indicate what is your elementary row operation, namely R1 goes to R1, R2 goes to this, and R3 again goes to the following, which we have indicated here. So, indicate what is the row operation that you perform to arrive at the system of equations at the next step. So, what happens here? R1 remains as it is, R2 remains as it is. The new R3 is obtained by performing the elementary operation, which is old R3 minus old R2 multiplied by this factor gives me the third equation in step 2. Now, look at this system. We observe that it is of the form matrix U multiplied by an unknown vector is equal to the right hand side vector B cap, where U is an upper triangular matrix. And therefore, you can solve this system of equations by backward substitution. We already know how we can obtain the solution of a system of equations when the coefficient matrix is upper triangular. So, from the last equation you can get what x3 is. Substitute that x3 in last but one equation, determine what is x2. Knowing x2 and x3 from the first equation, you determine what x1 is. So, you have the unknown vector x having components x1, x2, x3, which are determined using backward substitution procedure. So, Gauss elimination procedure essentially involves the following two steps, namely reducing the coefficient matrix A in the system Ax is equal to B to an upper triangular matrix using elementary row operations, and then the resulting upper triangular system will be solved by backward substitution procedure. So, let us illustrate this method by some examples. Let us consider the system of equations given by this, and let us try to solve this system by Gauss elimination method. And we know that this method involves two steps, namely reduce the coefficient matrix A to an upper triangular matrix, and then use backward substitution and solve for the unknown vector. So, in step 1, I take the first equation as it is, and that is going to be my pivotal equation at this step, and the coefficient of x 1 is the pivot at this step. And now I have to make the coefficient of x 1 in this equation and that of x 1 in the third equation to be zeros. So, what do? I take my new second equation to be as follows, namely I multiply the first equation by 1 by 10 and subtract it from the second equation. So, my old R 2 minus 1 by 10 R 1 will give me the new second equation. So, if I multiply this by 1 by 10 and subtract it from 1 times x 1, that will give me 0. So, I do not have a coefficient of x 1 here in the second equation. Then here I multiply this by 1 by 10. So, minus 1 by 10 and subtract that from this coefficient, and therefore, I will get the new coefficient to be 10 minus of minus 1 by 10. So, 101 by 10 into x 2. Then this coefficient will be 2 by 10. So, minus 1 minus 2 by 10, that will minus 12 by 10 x 3, and then 3 minus 4 into 1 by 10. So, 3 minus 4 by 10, and therefore, that gives me 26 by 10. So, that is my second equation. Then in the third equation, I have to make the coefficient of x 1, which is 2, to be 0. So, multiply the pivotal equation by 2 by 10 and subtract it from the third equation. So, my new third equation will be obtained as follows, the old third equation minus 2 by 10 times the first equation, which is the pivotal equation. So, I get 2 minus 2 by 10 of x 2 minus 2 by 10, that is 0. Then here 3 minus of minus 2 by 10, and so that is 32 by 10 x 2. Then 20 minus 2 by 10 into 2, then that will give me the coefficient as 196 by 10 into x 3, and 7 minus 2 by 10 into 4, that is 62 by 10. So, I obtain the new third equation as follows, namely the old third equation minus 2 by 10, the first equation, which is the pivotal equation. So, I have in the second step a system of equations to be given by the following, namely the second and the third equations. The second and the third equations do not have coefficient of x 1, the coefficient of x 1 in these two equations as zeros. And now I move to the next step. What do? I keep the first equation as it is and write down the second equation and treat this second equation as the pivotal equation at this step, and the coefficient of x 2 is going to be the pivot at this step. What do? I will have to make the coefficient of x 2 in all the equations which lie below the pivotal equation at this step to be 0. I have only one equation with me, namely this equation, from which I have to make the coefficient of x 2 to be 0. What should I do? I should take the third equation and then subtract from the third equation 32 by 10 by 101 by 10, namely which appears in the second equation, and that is what we have written. The new third equation is obtained by subtracting 32 by 101 of the second equation, and you will end up with a third equation in which the coefficient of x 2 will be 0, and that is what you see there. Similarly, take 196 by 10 minus 32 by 101 of minus 12 by 10, and that gives you this coefficient multiplied by x3. The right hand side will be 62 by 10 minus 32 by 101 times 26 by 10, and that turns out to be this. So, you observe that at this step you have a system of equations such that its coefficient matrix is an upper triangular matrix. So, step 1, namely the first step that is involved in Gauss elimination method is completed, namely reducing the coefficient matrix A in the given system Ax is equal to B to an upper triangular matrix. And the next step is to apply backward substitution procedure and then solve this system. So, the last equation gives you x3 as 0.269. The last but one equation gives you 101 by 10 x2 is 26 plus 12 by 10 x3. So, substitute for x3 and simplify and get what x2 is. And the first equation tells you 10 x1 minus x2 plus 2 x3 is 4. We already have computed x2 and x3, substitute and solve for x1, that gives you 0.375. So, you have been able to obtain the solution to the system of equations by Gauss elimination procedure. It is a powerful procedure, and you will see how it can be very efficiently used in obtaining solutions which are very accurate. Let us consider another example, because you may think that Gauss elimination method will work always. We will give an example where it fails to work. Then we will see how we can overcome this difficulty by what is called a pivoting strategy. So, explain what is a pivoting strategy and then employ what is known as partial pivoting strategy, and we will overcome the difficulty that we may come across while applying Gauss elimination method, and then solve a system of equations by Gauss elimination procedure with partial pivoting. So, let us explain this idea in detail in what follows. Let us now consider this example. So, solve the system of equations given by this by Gauss elimination method. Now that the method is clear, let us quickly apply the steps which are involved there. So, I retain the pivotal equation as it is, and then I will have to make the coefficient of x1 in the equations which appear below the pivotal equations to be 0. So, what should I do? I must multiply rho 1 by 3 by 1 and subtract it from rho 2. So, 3x1 minus 3x1, that will be 0. Then rho 1 by 3 and subtract it from the second equation. So, 3x2 minus 3x2, that is also 0. Then 3x3 must be subtracted from 4x3, that gives me x3. Then 3 into 6, 18 must be subtracted from 20, so I get 2. So, what did we do? We obtained the new second equation as follows: R2 minus 3 times R1 gives us the new second equation. R1 is taken as it is. Now, let us move to the third equation. I want to make the coefficient of x1 0. So, what should I do? Multiply the pivotal equation by 2 by 1 and subtract it from the third equation. Then you will get 2x1 minus 2x1, that is 0. Then x2 minus 2x2, so minus x2. 3x3 minus 2x3, so x3. 13 minus 2 into 6, 12, so that is 1. So, what did you do to obtain the new equation? It is R3 minus 2 times R1, and that gives you the new R3, namely the third equation. So, at step 2 you have obtained a system in this form. So, let us continue with Gauss elimination procedure. What do we have to do? We have to take the second equation at this step to be the pivotal equation. That is what Gauss elimination method tells. And what is the pivot? The pivot here in this step is the coefficient of x 2 in the second equation, which is the pivotal equation at this step. But I observe that there is no x 2 term here, because the coefficient a22 is 0 in this case, which is the coefficient of x 2. So, the pivot in the second equation, which should be taken as the pivotal equation, turns out to be 0 when we apply Gauss elimination procedure to the given system. So, what should I do in Gauss elimination method for the next step in reducing this system to an upper triangular matrix? I must, if I have the coefficient of x 2 as some a22 which is non-zero, then I must take that pivotal equation and multiply it by minus 1 by that coefficient and subtract it from this equation. But the coefficient there is 0. So, I simply cannot perform this step, and therefore, I observe that Gauss elimination method fails at this stage. Why does it happen? Because the pivot at this stage, namely a22, turns out to be equal to 0. And therefore, if at any stage of Gauss elimination procedure, if you observe that the pivotal element at that stage in the pivotal equation turns out to be 0, then you cannot proceed further and apply Gauss elimination method, and Gauss elimination method fails in that case. So, what is it that we can do in order to solve this system? So, let us look at this example and see what is it that we can do. Right? We observe that we have a third equation in which coefficient of x 2 is non-zero. So, this suggests that I can interchange row 2 and row 3 and take the third equation as the second equation and consider that as the pivotal equation at this step. Yes, I am performing an elementary row operation, namely interchange of equations is one of the elementary row operations. So, here I interchange the third row with the second row, namely bring the third equation to the second equation and the second equation to the third equation. So, I consider a system of equations now in which the first equation remains as it is. I have interchanged the third equation with the second equation. So, brought the third equation as the second equation. So, it is minus x 2 plus x 3 is 1. And the second equation comes here as the third equation. So, x 3 is equal to 2. Now, I look at the system. I observe that the system has its coefficient matrix to be an upper triangular matrix. And so, I can solve the system by backward substitution procedure. So, I get x 3 as 2, and so from here x 2 as 1, and from this equation x 1 equal to 3. So, the solution of the system has been obtained. But we did encounter some difficulty at our second step, where in the pivotal equation the pivot turned out to be 0, and therefore, we could not proceed further with Gauss elimination procedure, and observe that Gauss elimination method fails at this stage, and this can happen when you apply Gauss elimination procedure to a given system of equations. When does it happen? When the pivot in the pivotal equation at that stage turns out to be 0, or the pivot is a very small quantity, so that when we divide by that pivot, large round off errors might occur. In all these cases, we say that Gauss elimination method fails at that particular stage and employ what is called a pivoting strategy. So, we shall explain this strategy as follows.